What is all the hype with machine learning? Why should we even care about it? What can it do for us? That is what we're going to be discussing today. And if you'll notice, today we are not looking at a PowerPoint for our lecture. We're at that awkward point in the semester where it just becomes easier to use a text editor and some files to be able to teach a thing. So from this point forward, we more than likely will be spending the majority of our time actually coding and in a text editor and producing some kind of data. So today's topic is an introduction to machine learning and its potential applications. As always, I've got some references for you guys on lines 15 through 25. Three of them are from our last session: pandas, stats models, and scikit references. And then we have three that are about specific models that we'll be talking about today: the Gaussian or Gaussian, naive Bayes, PCAs, principal component analysis, and then mixture models or mixture clustering. And as we get to those, we'll dive into them a little bit deeper. For now, there's not too much to worry about. As far as your packages that you'll need today, if you have not already installed them, please install scikit-learn, stats models, and seaborn, and we will use all three of those today. Now, as always, let's get started with our virtual environment. So in my terminal over here on the right hand side, I'm going to navigate to my desktop, or not to my desktop, excuse me, to the proper location, and I'm actually already there. I'm going to ls, check my files. I want to activate this dat.sci folder, which is my working environment for our data science class. So I go source dat.sci/bin/activate, and we're on and running now. Let's get started with some imports here. Since they're just imports, I'm going to just shift enter on them and let them run themselves. We're going to import seaborn as SNS. We're going to import matplotlib as plt as plot. We're going to import numpy as np. Let's run those. So lines 53 or 54 through 56. Okay, so that's taken care of. Now we're going to import our data set. And if you guys remember, a few weeks ago we were working with a data set called Iris. And Iris is a very classic data science project that was from, I think, the early 1900s by Fisher. But it's a classic ecological paper where essentially they're studying the traits or features or characteristics of flowers and three different species of flowers. So they're all irises, but one is setosa, that's the name of the species, one's virginica, and one is called versicolor. And then we were measuring the sepal length and sepal width and the petal length and petal width. So we're going to be working with that data set again today. So we are going to import it here as iris, and all we have to do is say iris is equal to sns dot load underscore dataset, and then we tell it the name of our dataset. In our case, it's iris. There we go. And then we're just going to make sure the data loaded in correctly. Iris head, and looks fine. I don't see anything out of order. Maybe the data is sorted by species, but it doesn't really look like there's an exact pattern, an exact sorting pattern here. So nothing too exciting, but we do know it loaded in. It appears to have loaded in correctly. So now let's go ahead and get reacquainted with this data set. We're going to do some basic exploratory analysis, some basic plotting. So the first thing we'll do is run a pair plot. So we're going to go sns.pairplot, give it the name of our data set, iris. I'm going to tell it what the hue is. So what do we want to fill our little bubbles in with? In our case, we want to be examining the species aspect of our data set. And then we're going to tell it, I remember that this is not actually size anymore right here. This should be height. And we'll tell it its height. So how big do we want each of the boxes to be, or how big do we want our bubbles to be? There we go. Looks like it read that in just fine. Now let's go ahead and go plt.show to pop it up on the screen. There we go. Let's see if we can find any patterns in the data here. And immediately I see a pretty clear trend in the data. So in blue we have the setosa, in the orange we have the versicolor, in the green we have the virginica. And I do see a pretty clear pattern here of separation, at least in our data points. You can see that no matter what is plotted against each other, we always have the blue species, the Setosa, off on their own somewhere on the diagram. It's very, very rare, it looks like, that they're clumped right up against the green. Like this one and this one would be the closest where they're clumped up against the other two colors. Now for the orange, we can see the orange pretty clearly in every situation has separated itself away from the green based off of the characteristics of the flower. But we do see a little bit of overlap, maybe just like maybe 5 points or so that overlap with the green. But for the most part, there's still a pretty clear divide between the versicolor and the virginica. And then again, it appears that the virginica is the largest of the flowers, like has the largest features of the three species of flowers. And again, for the most part, off on their own, except we do see that little bit of overlap between the green and the orange. So just a small crossover region. Let's look at this data a different way. Let's check out a heat map. So the first thing we're going to do is specify our figure size. So we're going to say plot.figure fig size equals, and then we're going to tell it how big to make it, 15 by 15, and we'll close that off. There we go. Now we're going to go sns.heatmap, and we're going to say iris.core, comma, annote, which is annotate. Do you want it annotated? In this case, we do. We'd like to see the numbers. And then we're going to say CMap for color mappings. And ours is going to be in the red, yellow, green setup. There we go. And then we just have to say plot.show. Perfect. Okay, so again, similar trend. This time we're seeing less about the distribution of the data, and we are specifically looking at the correlation between features in the data. So if we look over here on the bottom left, we start with our sepal length. We can see that sepal length is pretty positively correlated with the petal length, 0.82. We also see that sepal length is pretty positively correlated with the the first one was petal width, the second one is petal length. So both petal features are strongly positively correlated to the sepal length. Now when we look at sepal width, the sepal width is actually negatively correlated to both the petal length and the petal width. And then when we move over into the petal features, we can see a pretty strong positive correlation between petal length and petal width. And what is it, 0.96. So that's pretty strong. So we have clear trends in our features here. We have positive and negative correlations that should allow us to separate out the relationships and be able to parse out the species and hopefully run strong regressions between to be able to properly categorize these species based on a machine learning model. But before we get there, the first thing we need to do is rebuild this data or reshape this data. So if you remember last week, we got to a point where I was using the wrong code. I was trying to reshape our y-axis, which didn't make sense. But when we're going through machine learning or regressions generally, and we're working with NumPy specifically, NumPy is expecting our array in a specific shape. I believe it's when we use the reshape function, it was .reshape -1, 1. And so it's expecting that sort of shape to our data for the training data set, or the feature data set, which would be like our table where, for instance, this case, we have sepal length, petal length, sepal width, petal width. Okay, so those things, it's wanting in a specific shape to be able to process it. So we need to reshape the data right at the beginning here to start. So the first thing we're going to do is create a data set called x_iris, which is going to be equal to iris, the data set, .drop, so removing a column, and we are going to drop the species out of our data set, and we're going to set the axis equal to 1. And the reason we're dropping species is because species is the y variable that we want to be able to predict. So we don't want our y variable in our x data set. It would be a confounding variable. So let's look at the shape of iris here. So x_iris.shape, and that is a array of 150 observations with 4 columns in it. All right, and that's exactly what we expect, because the original data set iris is shape 150 by 5. Oh, okay, so iris isn't callable in its initial state. That's fine. Now we got to do the same thing for y. So we're going to create a data set called y iris, which is iris, and then this one is specifically only going to contain the species variable. And if we look at the shape of y iris, we can see that it should be a one-dimensional array now. Yep, and there it is. Iris is a 150 comma nothing. So it's a one-dimensional array. And the reason that we had to do this is because, again, we're trying to make that feature table and our target vector. So what we've done now is x underscore iris represents this feature matrix shown here on the left, and the y underscore iris represents our target vector. So they're still lined up in in the order that the data set was originally presented to us. We've just chopped off the species aspect and turned it into its own target vector, and then left everything else together so we can model that data. So now what we're going to do is practice some basic linear regression and talk about linear regression again. And then we'll move into our more complex machine learning topics and machine learning pipelines. So the first thing we're going to do is set our state, or our seed. So we're going to say RNG, which is random number generator, is equal to np numpy.random state, and this time it's 42, just picking something. And then we're first going to compute a regression by hand. So we've talked about this already. This concept of y equals mx plus b. You've heard it your entire life. And that is an example of a linear model. Y is the thing that you want to predict, or your response variable, and then that is equal to mx, m being the slope of the line, x being your independent variable. The independent variable changes, which alters the response variable, and then plus b, and b is your constant. So it's just whatever number or point where the linear regression intercepts with the y-axis. So that's what we're going to start, and we're going to do it by hand, just to show you that we can do it by hand. So using our random number generator, we're going to compute or calculate an x value and create an x. So we're just going to say that x is equal to 10 times RNG, random number generator, times rand of 50. So we're going to ask for 50 values there. And then we're going to create a y, and y is equal to 2 times x minus 1 plus random number generator of 50 numbers. So that's our formula right there of 2 times x minus 1. That is our slope intercepts, or not our slope intercept, our linear model or linear regression. That's the form we've given the data there. So let's create our y. Now what we're going to do is plot x versus y and see if we can see any trends in our data. Boom, look at that. So we can clearly see that the data that we've just made up, because it is made up data, clearly is linear in form. It's a straight up and down correlation between points, and we can pretty clearly see that the points are clumped around some sort of center point. If we look at, so I would say that there is a strong correlation between these data points, and that we have a strong linear regression here, but we'll confirm that in a minute by looking at our coefficients and intercepts and such. And if we look at this line, we'll notice that it appears to intercept with the y-axis somewhere around maybe -9 or -1, and then it runs all the way over through 10. And again, we have 50 data points here. So that's our first linear regression. That's calculating linear regression by hand. Now what we're going to do is use a scikit model to calculate linear regression. So first thing we're going to do is pull in and decide what model we want to do. And so this is the same exact thing, right? We had already done a basic linear regression, so we are going to use a linear regression as our model in this case. So we're going to say from sklearn.linear_model import linear regression. There's that. Now what we're going to do is instantiate or activate our model. So we're going to say model equals linear regression, fit_intercept equals true. Run that. Then we're going to check on our model, see if it actually loaded, and it did load. Yes, of course it's showing empty here, but that's because when we instantiated or activated the model, we did not give it any characteristics or parameters. We just told it that we did want it to fit an intercept. So it should be empty at this point in time. Now what we're going to do is take our data from earlier, the X and the Y that we computed, and we're going to reshape them and then fit them on our model. So we are going to go ahead and say big X is equal to X square bracket of colon comma NP dot new axis, and we're going to close that off. There we go. So that's reshaped. Let's check it out. So X dot shape shows us an array of 50 by 1 dimensions. If we look at little x dot shape, we'll see that it was 50 comma nothing. So we've added and reshaped and built this data out a little bit into the format that scikit-learn is looking for. Now we can fit our model. So this is step 3. We're going to go model.fit. We're going to tell it what its variables are, which are big X comma little y, and it's going to fit those for us. Now we're going to look at the coefficients and the intercepts of our model. So model.coef underscore, and we get an array of 1.977, and then we're going to look at model.intercept underscore, and we get negative 0.9. Okay, let's see if that makes sense. On our plot earlier, I believe I said negative 0.9, and let's just double check. Yeah, it looks like maybe a negative 0.9, maybe negative 1, somewhere in that range. So that is plausible. It's reasonable to assume that the way the model is fitting at this point in time is correct. Now what we can do is take the model that we just fit and then begin to predict labels for the unknowns. So what we're going to do now is reshape, or not really reshape, but build a different data set essentially. And so we're going to use this function called linspace. This stands for linearly spaced vectors. So what we're telling it is to create a new object called xfit, which consists of numpy dot linspace, linear space vectors, and we're asking it to produce those on a vector from -1 up to 11. So within the exact range of the data set that we're working with here. So let's go ahead and do that. We're going to say xfit is equal to np.linspace, and then what our numbers are -1 comma 11. There we go. And then what we're going to do with xfit is actually reshape xfit just as we did up here to become big xfit. So we're going to say big xfit is equal to little xfit, and then square bracket colon comma np dot new axis, and then close off our square bracket. There we go. And now what we're going to do is take that big X fit and predict our Y fit based off of the big X fit. So Y fit is going to be equal to the model that we just calculated up above dot predict, the predict function. And then we're going to tell it what data it's using, and it's using big X fit. There's that. And now what we can do is plot the data. So we're going to say plot.scatter of X comma Y. Okay, that looks good. And then we're going to say plot.plot. So plot.plot is plotting a line essentially. And we're going to say of xfit comma yfit. So we're asking it to plot the line for our linear regression so we can actually see it compared to the points. And then we're going to say plot.show. There we go. So this is our data after it's been fitted and based on the line of best fit that we just calculated. And so we can pretty clearly see that the data fits pretty well. It's the line runs right down the center of the data. It still looks like it intercepts around -0.9 or -1. It's running up to 11 as we asked in the linearly spaced vector points. And it looks good. This would be presentable in a publication or whatever you needed, and you could add in your p-values, or not your p-value, excuse me, your r-squared values, as well as your formula, your formula right here on the screen, so that the user, the person that's viewing it, always had it. So that is our basic linear regression both by hand as well as using the scikit model. And you may not realize it just from us talking through it, but what you just did was calculate your first machine learning pipeline. And maybe you've heard that before, maybe you haven't. But when we talk about pipelines, all we're referring to is a set of principles or steps or an iterative process basically that we are going to use to do the same process over and over and over again based on some condition or parameter, and we're going to run our data from raw data through that pipeline and then produce the outcome that we're looking for. So you can have data analysis pipelines, you can have operations pipelines, you can have development pipelines, you can have whatever you want. But in this instance, we're working with a machine learning pipeline. And so our pipeline in this case basically had 5 core steps. The first was to choose our model. The second was to activate or instantiate our model, basically build the base model. Then we have to reshape the data into the features of the data set as well as the target, the thing that we want to be able to predict out of the data set. Then we fit the model based on the target and the features. And then lastly, we want to be able to predict on new data, whether it be real data or data that we've just made up. So that's the basics, okay? And this is what we're going to be focusing on more than likely for the next 2 or 3 weeks. So like 3 or 4 or 5 classes, let's say. And it'll change. Your pipeline always changes based on the conditions of use or the application. Sometimes you have a lot of pre-processing to do with your data, so your pipeline is like 17 steps of pre-processing and then 3 steps of actually running the machine learning model. So it always depends on the person, the place, and the time. But the really important part here is, do you need machine learning to do this? And the answer is no. We could do the exact same regression by hand, but we also could do it using a machine learning package or a sub package called linear model out of a machine learning package. And so the reason I bring this up is because in a lot of instances now we use machine learning as this hot button topic, and we want to apply it to everything and think that applying it to everything is going to be the greatest thing in the world. And in actuality, that's not the case the majority of the times. There's plenty of times in science or data science or business or whatever subfield you're in where you can get away with just doing a regular mathematical model. You could do regressions by hand and be able to predict some value based on that formula. The big benefit with machine learning is that the machine can see things and trends that you do not see. Their level of perception is different. So like if, for example, if we're talking about computer vision, if I showed you a picture of 100 humans, like a Where's Waldo, let's say we have a picture of Where's Waldo, and we give one to a person to find Waldo, and we give one to a machine to find Waldo that has been trained to identify people. And what we're going to notice is that the person that's using their eyes is basically having to scan the image back and forth and search for Waldo until eventually in X amount of time, they locate Waldo and tell you here he is. Whereas the machine, if it has been trained to identify faces or colors or a certain pattern, because that's what it's doing, it's been trained to find a pattern. Once it finds that pattern, it can focus on the pattern and lock in on it. And it can do that on the pixel level. So it can look at pixel by pixel and identify the patterning or the structure of that pixel in comparison to the other pixels and tell you where Waldo is in probably 1/3 the time as a human can. So that's what I mean. Pick your battles. You don't have to use machine learning because someone said to. Use your own thoughts and your own opinion and decide if it is necessary or not. There's plenty of cases where, again, you can get away by doing things by hand, and you also can always use a package like linear regression. So it's not like you have to use it by hand. You can still do your linear regressions computationally here. And I should have mentioned while we were talking about linear regressions, what we're practicing here is called the Gaussian naive Bayes. And this is, let's see if we can get you a definition here. This is a probabilistic machine learning algorithm used for classification functions based on Bayes' theorem. I say, okay, so what is Bayes' theorem? Let's go look it up. Bayes' theorem. Bayes' theorem is a probability formula or theory that basically calculates the likelihood that an event will occur based off of other conditions. And I'm sure you've seen this formula before, because anytime you talk about probability in math or statistics, you talk about Bayes' theory. So what this formula essentially says is that the probability of A given B is true is equal to the probability of B given A is true times the probability of A divided by the probability of B. And this can be switched around. So instead it could say the probability of B given A is true, and this one on the top row could say the probability of A given B is true. Okay, so you can flip things around, but the basis here is this is a way of calculating the probability that an event will occur. And so we use this to do linear regressions. And this, the Gaussian naive Bayes, represents our normal distribution that we talked about in a previous class. And the normal distribution is just our bell curve, that standard curve that we always talk about, where our mean is 0 and our variance is 1. Or excuse me, not our variance, our standard deviation is 1, I believe. Let me double check that. Normal distribution, variance. I was right the first time. The mean is 0, the variance is 1. So those are the assumptions, or one of the assumptions of the normal distribution. So that is linear regression. As I've told you before, linear regression is the basis for all continuous response variables that we want to predict. It is the key for most of statistics that we do at this point in time, or most data analysis, I would say. If we're predicting a continuous response to something, it is built on top of a linear regression. Okay, so now let's move into machine learning more. So we talked about last week the fact that we have different types of learning. So we have supervised learning, we have unsupervised learning, we have semi-supervised learning, we have completely self-supervised learning, and then we've got the mix of all the above. And don't get caught up in these learning concepts. That's exactly what they are. They're just concepts. The fact of the matter is you can use different types of learning in the same pipelines, as long as you're using the different types of learning correctly. So what I mean by this, for instance, is supervised learning. Supervised learning is the concept that we hand the machine a known set of data, and then it trains itself on that known set of data and compares that to the target vector and is calculating the weights of the model that way. And then once it has trained the model, you test the model using your X testing data set and your Y testing data set. And that's what we worked on last week, and we will continue to work on today. But my point with this is, in the supervised learning situation, you're handing it a known data set with labeled data, and then you're testing against a known data set, and then you're seeing how accurately you can predict based off of known values. Well, unsupervised learning is the exact opposite. You hand it data that it knows nothing about, and then based off of the nothing that it knows about the data, it uses either probability or some kind of other distance-based matrix to group and cluster and figure out who belongs together, and then be able to calculate how the features map onto the target vector, the thing that you want to be able to predict. So these are the two primary types of learning that we're going to be working with this semester. But again, remember that you don't have to use them mutually exclusive or exclusively. You could, for instance, use unsupervised learning, which typically focuses on reducing the dimensions of data and making it easier to find the relationships. We could use unsupervised learning in our pre-processing aspect of our data set, or to reduce the dimensionality of our data and only keep key features, and then come back and use supervised learning to exactly label all of our data points and then feed them into the model and be able to make predictions off of a supervised model. So you can mix and match. And again, it comes down to you, the user, and what your application is. So we're going to be practicing this supervised learning on our iris data. So the first thing we're going to do is import our model. So we are going to say from sk.learn model selection, import the train test split model. So this is, we used this last week. It does exactly what it says. It train, it test, and it splits your data set. And to do this, we're going to create variables xtrain and xtest, one to train, two to test, y train and y test, and then we use the train test split algorithm, and then we tell it what its data are. So we're saying it's pulling out of x iris, which we created way up above, and then y iris, which we created above and is just our species data, and then we're giving it a random state. And remember, you can within this, you can also specify and say like x will be 70% of the data and y will be 30% of the data, and we did that last week. But if you don't tell it the percentages of what you want x and y to represent, it'll just automatically choose a value for you, or there's a standard default value built into the model. So at this point, the data has been divided. We've got our pieces to our puzzle, if you will, that we need to be able to build our model. So that's what we're going to do now. So the first step here is deciding on what kind of model we should be using. What is our model class? And ours in this instance is going to be the Gaussian naive Bayes, which we were just talking about actually. So that's why I was talking about Gaussian naive Bayes when we were talking about linear regression, is because this is a model that's built into scikit-learn that you can use to predict a simple linear regression, or not to predict, to calculate a simple linear regression and then make predictions based off of your data. So that's the model we're going to use. We're going to load it in from scikit-learn, and then we're going to instantiate our model, which just means activate. So model is equal to Gaussian in B, and then our parentheses. That looks like it ran fine. We can double check. Yep, it ran just fine. It's empty, but that's exactly what we gave it. So we just turned it on, basically. Now what we're going to do is say model.fit, and then we're going to tell it what it wants to fit. So it wants to fit our X training data set, and then compare that to Y train. Okay, looks good. Now we're going to say y underscore model is equal to, and then we're going to ask it to make some predictions. So y underscore model is equal to model.predict, and then we're going to tell it it's looking at the y test data set and y model. Oh, excuse me, not y test. My eyes jumped ahead of my my typing. So it's going to be predicting based off of the x testing data set. There we go. And we could pop up this model if we wanted. I don't think it's going to show us anything interesting. And there it is. So the model basically outputs an array that is a bunch of different species. So what we've done is up here we instantiated the model. We turned it on. Right here we fit the model based off of the X training data set. And we can look at X train too. X train is a data set with our 4 features and the random numbers that were chosen, the random observations that were chosen to be in the training data set. So there's 112 observations of 150, and we have 4 features. So we use this X-train data set to fit the model, and then we also compared that to the Y-train data set. And the Y-train data set is the array that represents the same observations as what we have in the X-train data set, except the only thing in it is the target vector, which is our species. So we're using this to fit based on this. And after that, then we can actually make predictions. So we use the X testing data set, which the big X underscore test is, or big X test, excuse me. Big X test is just this testing data set that is all of the other features that were not included in the training data set. And so we took that information and made predictions on it and called that Y model. And based on those predictions, it gave us an output array. And now what we can do is test how accurate our modeling or our fit of our model is. And to do that, there are built-in analysis metrics in scikit-learn. And we'll talk about a couple of these as we learn machine learning. Today we're just going to be using an accuracy score, which is essentially literally a percentage or proportion of proper fit based off of your Y testing data, the data that you conserved from the beginning of the experiment, and then the Y modeling data that you predicted off of your X testing case. So we're going to load in the accuracy score there. And then we're going to use the accuracy function to compare Y test to Y model, and we see that we get 0.97368. So after one round of modeling, these 8 to 10 lines of code right here, we made a model or produced a model that is 97.36% accurate. That is incredibly powerful. And on top of that, we didn't have to do it by hand. Yes, we had to write a little bit of code and we had to understand the concepts, but overall, this allows for a high level of abstraction while still doing really quality work. And so that's one of the huge benefits of creating these pipelines is that you don't have to sit there with pen and paper and work through things. But again, we could have done this exact same thing with the iris data set by hand by calculating a linear regression. Would it have been as accurate? You never know. But the important part here is it's always about you in your use case and the application and what you need this data set to be able to do, or what you need this pipeline to be able to do time and time again. So that is supervised learning. Now we're going to move on to the unsupervised learning case. With unsupervised learning, yes, there are ways where you can predict based off of values and just give random unlabeled data in and be able to discover the relationships between your features and your target vector. But one of the other options with unsupervised learning is using it as a tool to reduce the dimensionality of the data. And dimensionality reduction is, I guess, a complex problem when it comes to mathematics, because basically you're trying to capture as much of the relationship in your data. So you're trying to maintain your feature representation, but reduce the amount of computational power and the complexity of your data by taking the number of dimensions down. So we're going to practice this to start, and we may use unsupervised learning concepts in our pipelines later on to reduce dimensionality of our data set. Like for instance, with our weather data we were working with a couple weeks ago, if you remember, we had like 12 to 18 parameters or something like that. And obviously, it's not going to be very easy for us to make a figure that has 18 axes that represent every feature to find the exact relationship. So using an unsupervised learning technique could take us down from 18, and maybe we end up with 5 useful dimensions or 2 useful dimensions. And that's just all about situational awareness. It's all about how do you need to use these concepts. And so that's what we're going to be focusing on today, but we will go into more complex topics. So luckily for us, because we've already worked with the iris data and we split it up above, we already have our data split and prepped, and I believe our variables are big underscore iris, and then we also have the other one, which I think is just y underscore iris. So those would be the 2 pieces of data that we're going to work on for this supervised learning case. Excuse me, unsupervised learning case. And so I popped them up over here. You can see again we have our feature matrix, and then we have our target vector under y-iris. So the first concept we're going to talk about is called principal component analysis, PCAs. And if you're unfamiliar with PCAs, I recommend you go to the link on line 23, and they have an explanation, a step-by-step explanation of PCAs. If you've had multivariable statistics or matrix algebra, you probably have already used PCAs, because matrix algebra is the basis for a principal component analysis. But basically what a PCA wants to do is a couple of key steps. Step 1 is to standardize your data set. Step 2 is to calculate covariance matrix. Step 3 is to calculate eigenvectors. Step 4, calculate eigenvalues. And then you can graph components. Okay, So standardizing your data. We talked about this last week when we did that normalization step in our machine learning example. Standardizing your data is just part of the process. Sometimes you have outliers in your data set, which really can skew the data or draw too much inference or relationship from a data point. And so to predict that, what we can do is, instead of having it on a scale of from 0 to 1,000, maybe we reduce the scale and standardize it based on a z-score, and we go down to 0 to 3 or something of that sort. And so it's a way of just standardizing, creating some normalization before you start to work with the data, so you're not improperly drawing conclusions from the data. Once you've standardized your data in a PCA, you can calculate the covariance matrix. And if you are unfamiliar with the concept of covariance matrix or matrix algebra in general, I encourage you to go to the link on line 23. If you've already had it, that's fine. It's not like a core concept that you'll need for everyday life, but it is the foundation for what we're getting ready to practice. So it's important to understand. But essentially, a covariance matrix is a way of comparing each dimension to every other dimension and then calculating the covariance. So how much of a relationship is there between dimensions or features that are not exactly the same and the features that are exactly the same. So for example, if we calculated the covariance between the petal length and the petal length, so p times p, that would be exactly the variance of that feature. So you end up with a standard matrix where the intersections, the diagonal, is essentially the variance of every dimension of your data set, and then you have your covariances on either side of the diagonal. And once you've got your covariances, you can calculate your eigenvalues, your eigenvectors. Once you've calculated your eigenvectors, you can calculate your eigenvalues based off of the vectors. And then you can put the eigenvalues and eigenvectors together to determine your number of principal components. So, or not even just your number of principal components, also the structure of your principal component. So the total, the features that are represented by that component. And one of the things that we do once we've gotten through this point where we've calculated our eigenvalues is we do what's called a scree plot. And a scree plot is a type of plot that basically shows you the number of axes or the number of elements or features found in your data set. And it shows you this kind of drop-off slope. Here, let me see if I can find one. And so here's an example right here. It shows you kind of this drop-off slope and tells you the percent of coverage of your variances based off of the percent or the number of components included in your data set. And so most of the time our goal is to keep it under 3 dimensions at a minimum, right? And we don't want to have to try to figure out how to graph 4-dimensional data. So if I can go from 18 dimensions down to 3 or even 2 dimensions and catch the majority of the representation of my features, then that's really good. And 2 is pretty much our standard. So like for instance, in this example, if we looked at this and we're like, okay, I want to capture 85% of the total variance in my data set. So if we look at this, we can say, all right, with principal component 1, I've got 40% of my data shown. All right, so that's clearly not enough. Then we can see principal component 2 covers about 20% of my data. So 40 plus 20 is 60%. So that's still not enough. It's not 85. Then principal component 3 adds in 12 more percent. So now we're at 72. And then 4 adds in another 8%. Now we're at 80. Then 5 adds in about 6%. So at 5 features, we finally get enough coverage. We finally get 85% or 86% of our data being represented. And so we use this scree plot as a tool to be able to determine the number of principal components that we should have on our data set. Now, that's how I was taught to do it. I do know a couple of people who do not use scree plots, and they automatically assume that they either want to have 2 or 3 axes, and so they just consider that a part of their model selection criteria. So they'll just decide, yes, I think I can capture it. I'm happy or satisfied with capturing it in 2, or I'm happy or satisfied with capturing it in 3 total vectors, or components, excuse me. So that's what we're going to be practicing here. So we're going to start here with principal components. As always, we're going to choose our model, which is the PCA. So we're just going to load that in from scikit-learn. Next thing we have to do is instantiate our model. So create it. So we're going to say model is equal to PCA, parentheses, in components, number of components or number of axes that we want to have, which will be equal to 2 in this case. Then we're going to say model.fit. So now we're going to fit our data and we're going to tell it what its data set is. And in this case, it is x underscore iris. There we go. Next thing we're going to do is transform the data to make it two-dimensional. This is not a step that we had in our pipeline up above, but it is a requirement for PCA. We need to have two-dimensional data to be able to work it here. So we're going to go x underscore 2D is equal to model.transform of x underscore iris. Oh, I spelled transform wrong. There we go. Oh, and I also messed up the name. There we go. Let's just delete the E here. There we go. Okay, so we've got our data transformed. Now what we're going to do is add labels to our data. So we're going to take the iris data set that we originally had, and we're going to add 2 new columns to it, PCA1 and PCA2. So up above in this model.transform, we basically created the data set of interest. So we took the weights of the model fit right here based off of X iris, transformed it into a two-dimensional structure, and now what we're going to do is take the two-dimensional the weights that we calculated using our PCA analysis and add those to our data set as PCA1 and PCA2. So those are going to be equal to big X underscore 2D of colon, comma, 0. And then also we're going to do the same thing for PCA2, except PCA2 will represent our ones. All right, that's done. Now all we have to do, we've already got the model fit and everything, we just have to plot the data. So we're going to go sns.lmplot linear model plot, and we're going to tell it what our x is. In this case, it's PCA1. And then we're going to tell it what our y is. In this case, it's PCA2. And then we have to tell it what our data set is. Data is equal to iris. We're going to give it a hue. The hue in this case is species. And then let's see what else we have. The last parameter here is fit regression. In our case, we are not fitting a regression this time. We are doing a dimensionality or multivariate analysis. So we'll just do false, enter that, and then we just have to say plot.show. And okay, so there's our data. So again, we've got Setosa in blue, Versicolor in orange, Virginica in green. With the Setosa, again, just as we saw with our pair plots, we can clearly see that Setosa is off on its own world. It's primarily being fit by, well, it's of course being fit by both, but we can see it's pretty much always under this -2 mark, and then it ranges, it has a broad range on PCA2. Whereas with Versicolor and Virginica, we kind of see this upward trajectory for both points, both colors. But we still see that little bit of overlap in the Versicolor and the Virginica that we were seeing in our pair plots. But with that, there's still clear separation between them. I would say right between these points, right there is where I would break them off. So we've done our principal component analysis. We again see a clear shape in our data. And we can go back to our data set, our figure from earlier, and make comparisons just real quick. All right, so here's our plot from earlier, and again, you can see the same trend we just saw. We always see blue off on its own. We see orange for the most part on its own, but there's that little bit of overlap between orange and green. So we are seeing separation between these species here, and we should be able to predict that separation. So with that is PCA. That's as simple as it is. So on the basis of unsupervised learning, if we are only using unsupervised learning as a dimensionality reduction tool, this is all it takes. It takes about 10 lines of code, 8 to 10 lines of code. If you need to predict based off of that dimensionality, or that reduced dimensionality, or create another model off of that reduced dimensionality, then you've got to add more steps to your pipeline. So in this instance, yes, of course, we're seeing that clustering, but we didn't provide an accuracy or a metric or anything to determine how accurate the clustering was based on a different aspect in our data set. So this is just for dimensionality reduction at this time. Now we're going to practice another type of dimensionality reduction, which is called Gaussian mixture modeling, or GMM. And GMM is one type of clustering. So really the category here is clustering. And there is a lot of different types of clustering. The two big ones I'd say would be the Gaussian mixture model, and then also the k-means clustering, but they're different. So k-means clustering basically takes your data and calculates the distance between every point as a finite number. So it says point A and point B are 0.74 meters away from each other. And it's going to do that for every single point in your data set, between every single point in your data set. And then based off of the distance that it calculates, it clusters the data points together. Whereas with the Gaussian mixture model, or the GMM, this is actually a probabilistic model. So instead of being based off of a finite distance, it is based off of a probability of that event occurring, or of those points being clustered. So Gaussian mixture modeling is sometimes referred to as a soft clustering technique, where we basically use the probability that these points in the same area are possibly in the same group. Okay, so there's positives and negatives to both. If you're like, for instance, with spatial modeling, let's use spatial modeling because there is distance in that. So if we're using spatial modeling, maybe there's a situation where, for instance, I need to know the exact distance between 2 points for route finding and finding the shortest path, and I could use k-means clustering to do that because it'll provide me an exact measurement of the distance between the points and properly cluster my routes together. I don't know, I'm making this up on the fly, guys. This is just an example. Whereas Gaussian mixture modeling maybe it wouldn't be as accurate. So maybe because 2 points are closer in proximity but have a road that is not as, but the road is not accessible from the main road or something, the distance is actually longer than computed in a Gaussian mixture model, but the probability is higher because of the proximity and the clustering that it uses for the points, and so it assumes that your shortest distance is X, and that is an incorrect prediction. So it just comes down to your use case. To your use case, but essentially what we're talking about is separating these things out into different pieces and clustering them together. And with k-means clustering, this is an example right here. So with k-means clustering, it is calculating the distance between every point and then locating the center point of a cluster, and then based off of the center point of the cluster, it is putting the points in the data set into that cluster. So it's based off of shortest distance to center, essentially, for the total number of clusters. And if we were running either of these clustering models or unsupervised learning models, and we iterated over them, over time we would expect the clustering to get better. So let's say instead of running it one time, we run it 500 times. We'd expect the accuracy of the clustering to improve over time. And that's fairly standard, right? That's one of the things that we worked on last week, is we were iterating over the model and iteratively adding features instead of adding all the features at the beginning. So time is also a component here. We commonly would call that like the epoch. How many generations do we want it to go through? Now, with Gaussian mixture modeling, again, very similar concept where it wants to cluster, but it wants to create clusters. But instead of creating clusters based on distance, it's creating clusters based off of probabilities. And like I said, this is considered to be a soft clustering technique because it's all based off of proximity. So for instance, like in our data set, and we'll see this here in a minute, in our data set we have that overlap between the versicolor and the virginica, and we're going to use this Gaussian mixture model to cluster them. Well, do we think it's going to be 100% accurate the first time if we know that there's that overlap? My guess is no, but we'll find out. And that's one of the issues here, is because it's a proximity, based on proximity, we can end up incorrectly clustering things. But that happens with every algorithm. So again, it always comes down to use case and application and personal preference. But let's go ahead and get started on this GMM. So first thing we're going to do is choose our model, which is the GMM. So we're going to import that from scikit-learn. Next thing we can do is instantiate our model. So we're just going to say model is equal to GMM, and then we're going to tell it the number of components is equal to 3, because we have 3 species that we eventually want to be able to predict. So we're going to have 3 clusters. We want to cluster it based off of species. And we have to tell it the covariance type. You can have full and partial covariance, I believe. In our case, we're going to use full covariance. So we'll instantiate our model, just say model equals GMM, in components equals 3, comma, covariance equals full. There's that. Then we just fit our model, step 3 in our data set. So model.fit of x underscore iris. There's that. Now we're going to make predictions. So we're going to say y underscore GMM is equal to model.predict of x iris, which is the exact same thing. Notice here we're using the same pipeline for both PCA and for our GMM. So the pipeline stayed the same. The steps kind of change. The only difference up here for PCA was we had to do the transformation, but that transformation will also help us down here because now we have the PCAs that we can use to plot this data. So now we've made it through step 4. We've determined our clusters. We've predicted our clusters based off of big X underscore iris. Now what we're going to do is take those predictions, which we can show you, y underscore GMM. Okay, 1s, 0s, and 2s, right? So these just represent if there's something there, if there's not there, based off of our predictions off of X iris. So we're going to do the exact same thing we did right here where we added labels to our data. We're going to add labels to the iris data. So we're going to say iris and create a new category or column called cluster, and that'll be equal to y underscore GMM. And then we are ready to plot. So we're just going to do sns.lmplot, and we're going to say x is equal to PCA1, y is equal to PCA2, data is equal to iris, hue is equal to species, column is equal to cluster. Fit regression is false. We do not want to fit a regression this time. And once that's run, it looks like it ran in fine. We're going to do plot.show and take a look at our clusters here. And again, there we go. We're seeing the exact same trend that we saw earlier on our PCA plot, which makes sense. We can't compare two at once, which makes sense. So we're seeing in cluster 0, we have the virginica and a couple of those versicolors snuck in like I thought they would. 1, 2, 3, 4, 5. So we've got 5 points or five observations that are incorrect predictions here. We've got cluster 1, which only represents Setosa, and that makes sense. Setosa was very clearly off to the side. They had the closest relation, or the most obvious separation from the rest of the species, as well as a pretty close relationship within the species. And then we see the versicolor, again, pretty clear structure. Again, we did lose those few points to cluster 0, but overall there's an obvious trend in this data. So this is our simple clustering technique based off of the GMM, so a soft clustering technique. And if we wanted to improve on this and get these virginicas, or excuse me, these versicolors out of the wrong cluster, we would have to iterate over this model or figure out another way to tell the computer that these points do not belong in cluster 0, they belong in cluster 2. But one of the issues with that is the reason these are being plotted in cluster 0 is because we had some outliers in the versicolor, and based off of the versicolor data set, it is there's a probability that these points these data points could come up again. They could exist again out in nature. It's already happened once and we were able to record it, so we could accidentally record it again, and we need to make sure we can accurately tell that that is a versicolor, not a virginica, in a future instance. And so we'd have to figure out how to incorporate that in the model, or we'd have to run the model again and again and just keep going through it So let me run it one more time and see if anything good happens. I don't think so. Yep, exact same thing. 1, 2, 3, 4, 5. So, yep, we'd have to update the model. We'd have to tell it specifically how to remove those for the cluster. Again, remember though, I've only ran it twice. I mean, in some instances, you could run a machine learning. The epoch could be 100,000. You might repeat that same model 100,000 times with different variations. So, it's not surprising to me that this is clustering incorrectly. The fact of the matter is, though, what's important here is that we just practiced our first unsupervised learning model, and with relative ease overall. So that is what I had for you guys today. I hope you enjoyed this. We're going to be spending a couple more weeks working on AI, machine learning, those kind of aspects. And we will, like I said, we'll be working primarily from text editors from this point forward. One tool we'll be adding in next week out of necessity is probably Colab. If you've never heard of it, it's a Google tool that offers free collaborative learning environments for, it's basically like a Jupyter notebook but built on Google's resources. So you have open source TPUs and GPUs, graphics processing units and tensor processing units, which are super useful for machine learning. It speeds up the applications by a lot, by you know I don't know, at least double. I would say tenfold, but it probably depends on the amount of data you're working with. So we'll eventually have to move into that environment just to make sure that everybody has equal access to information and to processing power. But we'll get there when we get there. For today, thank you so much for being here with me. Thanks for giving me your time. I hope you have a great rest of your week, and I will see you next time.